also neoplasm. So amputation is now redirecting cells that would normally give rise to other tissues to now give rise to the pharynx problem. So how is that all regulated? And I think that one of the ways at which it happens is by the activation of this gene FOXA polymerase, which is going to tell us a great deal about how to regenerate endodermal tissues in our cells and other organs. So this is just a computation showing that there is a significant increase in the number of stem cells that are now expressing this marker. And so we now think that organ regeneration decisions, how you make a new tissue from scratch, is actually taking place in the stem cells themselves, as opposed to anywhere else. It is the stem cells that are making a decision, so to speak, to become endodermally mutated to give rise to the pharynx problem. Okay, so what happens if you get rid of FOXA? If you get rid of FOXA and you don't get a pharynx, I showed you earlier that it's a burst of proliferation. The cells, the neoblasts are sensing that there's a tissue missing, so they make more and more cells. But in the absence of FOXA, that surplus of proliferating cells cannot give rise to a pharynx. So what happens to those cells? Do they undergo apoptosis? Do they die? Or do they go on and do something else? So what we see is that they actually give rise to these bumps in these animals. And when we look at the tissues that are arising in these animals, they're essentially tissues that are associated with some aspects of the pharynx, neurons, this is a neurotransmitter, and of course in FOXA we see no detection of FOXA, which is really abnormal growth. So what happens now is that surplus of cells don't know what to do, and they differentiate primarily into neurons and muscle. And they give this construct here that look anything like a pharynx problem. So FOXA RNAi animals really forming this spike is actually in the center of the animal is a consequence of abnormal differentiation of the neoblast to regenerate the pharynx problem. So what we see now is that this outgrowth is enriched for disorganized neurons and muscle, as I mentioned to you earlier. So here's the control, and you can see now the affected animals, essentially showing that these spikes are full of neurons and also full of muscle. Suggesting then that the entire organization of all the cells to provide the structure of the pharynx and to scale the pharynx properly is seemingly dependent in its majority on the expression of the gene FOXA, which is really a remarkable finding because it allows us now to use that as a point of departure to dissect this problem much more specifically. So this allows us then to set up a series of genetic cascades of gene expression to explain how the different cells get co-opted and channeled to give rise to the pharynx problem. So the genes that are expressed in phase 1 are the genes that we think are required for the proliferation of the neoblast. The genes that we find expressed in phase 2 are genes that actually are giving rise to cognitive progenitors, so they give rise to the cells that will now become pharynx. And then of course the genes in phase 3 are the ones that take these progenitor cells and differentiate them into the appropriate form and function. And so that allows us then to draw this map where a single cell, a stem cell, expressing these genes, okay, that I showed you earlier in the process, somehow come together to activate these other covalent genes that will now take these progeny of the neoblast to give rise to parental progenitors. And these parental progenitors, through mechanisms we don't understand, come together and begin to give rise to the pharynx proper, which is entirely regulated by this gene FOXA. As you can see, the complexity of the process diminishes the more and more committed the cells become. So we can now work our way forward and backwards in trying to understand how all these structures acquire their face, how they come together, and how they scale and functionally integrate to the pre-existing tissue to allow for full restoration of function and activity in animals that were injured by the removal of their agents. So what's happening at the organismal level? How are these decisions made? What are the signals that allow stem cells to produce the right type and the right number of cells such that the animals maintain the proper form and function? And this is what we don't know. But we suggest the possibility that once the pharynx reaches a particular size, it sends some kind of signal back to the stem cells proper that prevents them from making more of this tissue. So we don't end up with extra long ranges or extra short ranges. And those kinds of mechanisms are the ones that we're going to have to uncover in the years ahead to try to understand how the scale and proportion come together. So we don't know what the signals are, and that's the fun part of this business, is that we can now begin to really dissect this at a very high level of granularity and a very detailed mechanistic description of the process. So in conclusion, it is now possible to experimentally interrogate aspects of scale and proportion using planarians as a model system, and how these organisms regulate these processes to allow the animals to assume and acquire their appropriate allometric proportions. Secondly, the genes that are associated with specific organ systems and their regeneration can be identified. We can dissect them. So we can systematic analysis of how regenerated organs scale and are functionally integrated to pre-existing tissues. So I hope that this was informative to you, and thank you very much. Hello everyone, my name is Alejandro Sanchez Alvarado. I am an investigator with the Stauch Institute for Medical Research and the Howard Hughes Medical Institute. And for the next few minutes, I'm going to give you a summary of what we have learned in the past few years about the planarian stem cells, also known as neoblasts. So the term neoblast was coined by a graduate student in Greenmore College in 1893 to refer to these undifferentiated cells that are found distributed throughout the body plan of the planarian anatomy. And these cells are responsible in great part for the immense capacity to regenerate missing body parts after amputation in these animals. So what you see here is essentially a 7-day progression of an animal that was decapitated, and you can watch how the tissues that begin to form in front of the bed of amputation begin to differentiate into something that looks like a planarian hair. These cells are broadly distributed throughout the anatomy of the organism. They're labeled here in green, and you can see, for example, that they are in essentially every part of the animal, with the exception of the tip of the head of the animal per se, and the pharynx proper. And these are the only two tissues that, when amputated from the animal, will not regenerate a complete animal. We know this from the work of Morgan, G.H. Morgan in 1898 and 1901. But the rest of the tissue, as long as you have this green cell, this neoblast, they'll actually launch a regenerative response to restore the form and function of the fragment into a complete animal. So what do these cells look like? These cells are highly undifferentiated. They're relatively abundant. You can see here the nucleus in pink. This is very few electron-dense material by the electron micrographs, suggesting that most of the DNA is in a relaxed state. It's non-condensed, which means that DNA is totally open for business. Transcription should be taking place in a variety of ways as to allow the cells to differentiate in the 40 to 50 different cell types that make up the anatomy of this organism. The cytoplasm is highly basophilic, so it's filled with RNAs, mitochondrial RNA, ribosomal RNA, messenger RNA, and probably long-non-coding RNAs and microRNAs and the entire population and types of RNA in cells. What is remarkable about these cells is that they're not rare. They're actually very abundant, which you can rarely see by just looking at this organism where the neoblasts were labeled. So these neoblasts correspond by anatomy alone, by morphology of the cell, to about 25% of all of the cells in this animal. That is a gross exaggeration of a particular cell type, particularly an undifferentiated cell type that can potentially turn into any tissue type in these animals. Secondly, these are the only dividing cells in planaries. Again, another exaggeration. Normally that's not the way it works, but in these animals you have stem cells, which are the only ones that divide, in sexually reproducing animals, and then the other cells, which are the differentiated cells, which are entirely post-mitotic. They will not divide anymore. And then we also now know that they're not only collectively coding, but also of the cells, when you remove this fragment from the animal, for example, then this little square can regenerate a complete animal, and then those few neoblasts that are present in there will divide, proliferate, and differentiate into all the tissue cells that are missing. But more recently, a prior postdoctoral scientist in my lab, who's now running his own laboratory at the Whiting Institute at MIT, demonstrated that you can remove an individual cell from these animals, put them back into an animal in which all the neoblasts were eliminated, and with some frequency, that individual cell is capable of restoring all of the cells and all of the tissues to these animals, settling the suspicion, the long-term suspicion, that these cells really contain the capacity to be, if not totally, at least pluripotent, and capable of restoring and producing all the cell types in these animals. So that makes these cells particularly interesting, because what it tells us is that they have figured a way to regulate the genomic output into very specific products to give rise to muscle, or in other instances neurons, or in other instances epithelium, and so forth and so on. And we need to understand how these cells are managing all this information to produce tissues in the right number and of the right type to allow the animal to be recognizable as a planarian. So we know that amputation is capable of activating the proliferation of these cells. So at any given time, these cells are divided. At any given time, in fact, 2% of all neoblasts are entering the cell cycle. This is a really fast and furious activity, but amputation actually increases that rate to even higher numbers. And I'm going to show you that right here. You can see here a head regenerating tail, which is the head fragment. You can see now a trunk that is now going to be regenerating a head and a tail. And then you can see a tail fragment, which is essentially going to eventually regenerate a head right here. Okay? So when